All right, welcome to the first lesson in Unit 7. Remember, Unit 7 covers right triangles and trigonometry. Right triangles are one of the most common shapes that we work with, and so there's a lot that we can learn about them and understand about them. In this lesson, we'll look at something called the Pythagorean Theorem. Most likely you've heard of or worked with the Pythagorean Theorem before in a previous class. So if you remember, it says that if you have a right triangle, like what we see here in this image, we know it's a right triangle because of this little half red square here in the corner that tells us this is a right angle, and so this is a right triangle. If you have a right triangle, the square of the length of the hypotenuse, that means the longest side, is equal to the sum of the squares of the lengths of the legs, the other two sides. And so you have this really common or famous formula. It's written here as c squared equals a squared plus b squared. Maybe you recognize it as a squared plus b squared equals c squared. And what that's saying is that if I just take each of those shorter sides and square them individually and then add them together, that will give me the square of the longest side. And so why we use the Pythagorean theorem is to help us find unknown side lengths of right triangles. So you've got the two shorter sides here in the hypotenuse. If I know at least two of them, I can use this formula to help me find the third one. And that again is only for right triangles. And so that's why we'll use the theorem. Something also to note is something called a Pythagorean Triple. As I said, right triangles are really common. And so we understand that there's a lot of patterns when working with right triangles in the Pythagorean Theorem. And what you're seeing here are what we call Pythagorean triples, which is just three numbers, the lengths of each of the sides of the triangle, that all satisfy that Pythagorean theorem, c squared equals a squared plus b squared. So like if we look at this first one here, 3, 4, and 5, those are each a side length of a right triangle, and they satisfy that Pythagorean theorem. Now the thing that makes that a Pythagorean triple is it satisfies the equation, but then also I can multiply those numbers by any other numbers. So if I take 3, 4, and 5 all times 2, that's 6, 8, and 10, well that also is still a right triangle. Those are the side lengths of a right triangle. Those are just multiples of this Pythagorean triple. If I take them times 3, 9, 12, and 15, then that is still a right triangle. And so what we do here is, you're not necessarily going to memorize all these numbers, but the more that you work with it, you'll start to notice some of the patterns, and some of these triples start to show up a lot more. And so you can start to recognize them pretty easily. So that's just something to note with the Pythagorean triples. We'll look at another example in just a second, but just to show you, this is what you're going to be doing with the Pythagorean theorem. You're going to be finding unknown side lengths of right triangles. So you see here in this example, I have two of the sides, and I want to find the third one. So I'm going to plug in my values and my variable into my Pythagorean theorem, and then solve to find the variable. And that's what we'll be doing. We'll look at an example in just a second. One other thing that we'll need to know for this lesson is the converse of the Pythagorean theorem. And that kind of works like the reverse. In the Pythagorean theorem, it said that if we have a right triangle, then this equation works. C squared equals a squared plus b squared. The converse says it the other way. If this equation works for a triangle, then we know that triangle is a right triangle. So what that means is that if I have this triangle, and I'm not sure if it's a right triangle, I can check by seeing if this equation works with the side lengths, with the two legs squared individually added together equal to the square of the hypotenuse. So it would be something like this. If I wanted to know if this triangle is a right triangle, I can take the two shorter sides, square them, add them together, and see if that equals the square of that third longest side. If they do, then the triangle is a right triangle. If they don't, then it's not a right triangle. And so we'll also look at some problems like that. Now let's go ahead and look at some examples. So what we're looking at here is on page 5 in your note packet. And we're going to look at a couple examples where we're using the Pythagorean theorem to find an unknown side, and also to use the converse of the theorem to determine if we're looking at a right triangle. So let's look first here at number 8. And the instructions are to find the value of x, and then tell whether the side lengths form a Pythagorean triple. So what I have here is this right triangle. You see right there, that's right triangle. I know two of the sides, 5 and 12, and those are also my legs. Okay? I know that these are my legs. And this here is my hypotenuse. Now how do I know that it is my hypotenuse because it is across from that right angle. Okay? So that makes it the longest side in this triangle. And that's important to know for when I'm setting up the formula. So our Pythagorean theorem says a squared plus b squared equals c squared. And we're going to try to figure out what the hypotenuse, that's our x. So I'm going to plug in my other two legs, 5 and 12. So that's 5 squared plus 12 squared equals c squared. Okay? Well, actually, let's, instead of calling that c squared, we'll call it x squared because that's what our variable is here. And then I'm going to simplify. 5 squared is 25. 12 squared is 144. And x squared is just x squared. 25 plus 144 is 169, equal to x squared. And now here, in order to get it just to be x, because that's what I'm looking for, what is x equal to, I have to square root. Okay? I have to square root both sides of the equation. It's like when you're solving for x and you have to divide on both sides or multiply on both sides. We're having to square root on both sides in order to solve for x. So the square root of x squared is just x. And the square root of 169, you could do that in your calculator, or if you know it, is equal to 13. And so that is what the value of x is. That is the length of this side right here. That's 13. So that's the first part, plugging in the values into the formula and solving for x. And then we need to determine do the side lengths form a Pythagorean triple. You could check your notes to see is this one of the normal Pythagorean triples, and yes it is. The other way to think about it is, are they all whole numbers? 5, 12, and 13. Yes, those are whole numbers. And so yes. And so that is how we would go about this type of problem. So again, just using the theorem to help us find that unknown measurement. Let's look at another one. Let's look at number 10 right below it. So again, we have a right triangle here, okay, and we have the two legs, and we're looking for the hypotenuse. So let's go ahead and set up our formula, a squared plus b squared equals c squared. I write the formula each time just so it's there right in front of me. You don't necessarily have to do that if you remember it, but it's good to do if you have trouble remembering it. So our two legs are 4, so that's 4 squared, and 6, that's 6 squared, equal to x squared. 4 squared is 16, 6 squared is 36, equal to x squared. 16 plus 36 is 52, equal to x squared. And so I'm going to square root that on both sides, and so x is equal to the square root of 52. Okay? And so we could just leave our answer like that, the square root of 52. But what we can also do, remember what we reviewed at the beginning of this unit, is simplify that radical. And so if you recognize that the 52, the square root of 52, is equal to the square root of 4 times the square root of 13, because 4 times 13 is 52. Okay, 4 times 13 is 52, so the square root of 52 is the square root of 4 times the square root of 13. Square root of 4 is 2, square root of 13 is a decimal, and so we would say x is equal to 2 square root of 13. And so that is the length of that hypotenuse, 2 times the square root of 13. Now, is this a Pythagorean triple? Well, if you remember from the first one, 5, 12, 13, those were all whole numbers, so that means it was a triple. But since we have our hypotenuse is not a whole number, that's 2 times the square root of 13, then this is not a triple. So we have found our triangle here, the hypotenuse to be 2 times square root of 13, and that is not going to be a Pythagorean triple. Alright, so this is just on the next page of your notes. The directions say to tell whether each triangle is a right triangle. So we have a triangle here, but we don't know if it's a right triangle, right? There's no symbol there to tell us it's a right triangle, but we have all three sides. Well, this is where we can use the converse of the Pythagorean theorem by setting up the formula and determining, does it come out to work? Does it come out to be equal? Okay? And so I first determine, which are the shorter sides, which are the longer sides. It might be hard to tell with that if that's the longer side, but it is. If you put into your calculator the square root of 95 and then times it by 4, you would see that that's longer than 15 and 36. And also the general structure of this triangle, you can tell that this is the longer side. So what we're going to do is plug in to our formula. our two shorter sides will be a and b here, 36 and 15. So that's 36 squared plus 15 squared. It doesn't matter which one's a and b. If you know those are both the shorter sides, it won't matter which is a and b. You can flip them around. And then c squared will be 4 times the square root of 95 squared. And then I'm just going to simplify this using my calculator to see if these come out to be equal. So after simplifying this, I find that on the left-hand side of the equation here, the legs added up to be 1,520, and the hypotenuse simplified down to 1,520. Or this was 521, this was 520. So just a little bit off. And so because these are not equal, right? Because these are not equal to each other, put a slash through that, this is not a right triangle. So in order for this to be a right triangle, those would have to be equal to each other because that would mean that the theorem works, or the equation works. They fit the equation. But since they're not, the equation doesn't work, and so this is not a right triangle. And that's how I would go about completing that type of problem. One other thing you might note is that the square of a square root, the square root of 95 squared, is just 95, right? The square and the square root cancel each other out, so pay attention to that as well. But this is your final answer.